A prism is an optical apparatus made of transparent material with flat and polished surfaces that refract light. The most commonly used prism is a triangular prism which has 2 triangular and 3 rectangular surfaces. The 2 rectangular surfaces through which light is refracted are called the refracting surfaces of the prism. The cross-section of a prism that is perpendicular to the refracting surfaces is called its principal section. Here, ABC is the principal section. The faces AB and AC represent the 2 refracting surfaces. The angle between the 2 refracting surfaces is called the angle of the prism or the refracting angle. Let us derive the expression for angle of deviation for triangular prism. Consider a light ray PQ incident on the refracting surface AB at an angle of incidence I. Let NN' be the normal to the surface AB at Q. The ray of light refracts at the face AB and QR represents the refracted ray. Let the angle of refraction be R1. The refracted ray QR is incident on the refracting surface AC at R and emerges along RS from the prism. Let NN" be the normal to the surface AC at R. For refraction at the surface AC, let the angle of incidence be R2 and angle of refraction be E, which is also known as angle of emergence. The angle between the incident ray PQ and the emergent ray RS is called angle of deviation D. In the quadrilateral AQNR, angles AQN and ARN are right angles. Hence, angle A plus angle QNR is equal to 180 degrees. Let this be equation 1. Since the sum of the angles in a triangle is equal to 180 degrees, in the triangle QRN, R1 plus R2 plus angle QNR is equal to 180 degrees. Let this be equation 2. From equations 1 and 2, we can write that angle A is equal to R1 plus R2. Since angle A is the refracting angle of the prism, we can write that refracting angle A is equal to R1 plus R2. Let this be equation 3. In the triangle MQR, angle MQR is equal to I minus R1 and angle MRQ is equal to E minus R2. Since in a triangle, external angle is equal to the sum of the 2 opposite internal angles, for the triangle MQR, we have D is equal to I minus R1 plus E minus R2, or D is equal to I plus E minus R1 plus R2. On substituting the value of angle A from equation 3, we get D is equal to I plus E minus A. Let this be equation 4. Since the angle of refraction depends on the wavelength and refractive index of the prism, we can say that the angle of deviation D depends on the refractive index of the prism, wavelength of the incident light ray, refracting angle of the prism, and the angle of incidence. The angle of deviation increases with increase in the refractive index of the material of the prism. More the wavelength of the incident light ray, less is its deviation. Experimentally, it has been found that the angle of deviation decreases with increasing refracting angle. If the variation of the angle of deviation is plotted against the angle of incidence, the graph is as shown. As the angle of incidence increases, the angle of deviation initially decreases, reaches a minimum value, and then increases. The minimum value of deviation is represented by dm and is known as the angle of minimum deviation. Hence, corresponding to any value of the angle of deviation other than dm, we have two angles of incidence. These two angles correspond to I and A. That means, if one is the angle of incidence, the other will be the angle of emergence. Interchanging I and E does not make any difference to the value of deviation d. If PQ is the incident ray, then RS is the emergent ray, and if light enters the prism along SR, it emerges from the prism along QP. If the incident light strikes the prism at an angle that makes the deviation minimum, then the prism is said to be at its minimum deviation position. When the prism is placed at its minimum deviation position, it is found that the light ray passes through the prism symmetrically and is parallel to the base. In this case, the angle of incidence, I, is equal to the angle of emergence, E. Because of the symmetry, we can also write that R1 is equal to R2 and let them be equal to R. Hence, when the prism is at its minimum deviation, equation 3 can be written as A is equal to 2R or R is equal to A by 2. Equation 4 can be written as dm is equal to 2I minus A or I is equal to A plus dm by 2. But the refractive index of the material of the prism, N21, is equal to sin I by sin R. On substituting the values of I and R from equations 5 and 6, we get N21 is equal to sin A plus dm by 2 by sin A by 2. Let this be equation 7. Using equation 7, the refractive index of the material of the prism with respect to the surrounding medium can be found accurately. In this method, the values of A and dm are found experimentally. If the refracting angle of the prism is small, then the value of the minimum deviation is also small. But we know that for small angles of theta, sin theta is approximately equal to theta. Hence, we can assume that sin A plus dm by 2 is approximately equal to A plus dm by 2, and sin A by 2 is approximately equal to A by 2. Substituting these values in equation 7, we get N21 is equal to A plus dm by 2 by A by 2. On simplification, we get dm is equal to A into N21 minus 1. Therefore, for prisms of small refracting angles, minimum deviation is small and is independent of the angle of incidence. Let us apply these formulae and solve some examples. Example 1. A ray of light incident at an angle of 50 degrees is refracted through a prism at the minimum deviation position. If the angle of the prism is 60 degrees, find the angle of minimum deviation and the refractive index of the prism. In this problem, it is given that I is equal to 50 degrees, A is equal to 60 degrees. The prism is at its minimum deviation position. We know that deviation d is equal to I plus E minus A. When the prism is at minimum deviation, dm is equal to 2I minus A. On substituting the values of I and A, we get the minimum deviation equal to 40 degrees. Substituting the values of A and dm In equation 7, and on further simplification, we get the refractive index equal to 1.532. Example 2. A prism of refracting angle of 60 degrees made of glass of refractive index 3/2 is immersed in water of refractive index 4/3. Find the angle of minimum deviation for a light ray passing through the prism. In this problem, it is given that refracting angle A is equal to 60 degrees. Refractive index of glass Ng is equal to 3/2. Refractive index of water Nw is equal to 4/3. As per equation 7, N21 is equal to sine A plus dm/2 by sine A/2. Since the prism is in water, Ngw is equal to Ng by Nw. On substituting the respective values, we get 3/2 by 4/3 is equal to sine 60 plus dm/2 by sine 60/2. On simplification, we get dm is equal to 8.46 degrees. Observe the coin placed in an empty container. Rays from the coin enter the eye and make it visible. If the eye is lowered, at some point, we lose sight of the coin. As water is filled in the container, the coin is visible again. This is due to refraction of light. Some of the rays of light from the coin, while traveling from water to air, bend at the water-air interface and reach the eye. This makes the coin visible again by giving the impression that the object is at a different location. While passing from one transparent medium to another, an obliquely incident ray of light bends at the interface of the two media. This phenomenon is called refraction of light. Refraction of light is due to the fact that the speed of light is different in different media. The extent of refraction can be found if we know an optical property of the medium called refractive index. Refractive index or absolute refractive index N of a medium is defined as the ratio of the speed of light in a vacuum to its speed in the medium. It is a pure number with no units and dimensions. If the speed of light in a medium is v, then N is equal to c by v. Let this be equation 1. Note that the speed of light in a medium is inversely proportional to its refractive index. For example, the refractive index of water Nw is 1.33 and that of the glass Ng is 1.52. Since refractive index of glass is more than that of water, the speed of light in glass is less than the speed of light in water. If the refractive index of a medium is greater than that of another medium, then the first medium is said to be optically denser than the second medium. For example, glass is optically denser than water. Note that optical density of a medium is different from its mass density. The optical density of a medium is its refractive index and depends on the speed of light in it. Whereas mass density is the mass per unit volume. When light travels from denser medium to a rarer medium, its speed increases and bends away from the normal. On the other hand, if light travels from a rarer medium to a denser medium, its speed decreases and bends towards the normal. The relationship between the angle of incidence, I, and the angle of refraction, R, is explained by the laws of refraction. When light travels from medium 1 to medium 2, 1. The incident ray, the refracted ray, and the normal to the interface at the point of incidence all lie in the same plane. 2. For a given pair of media, the ratio of sine of the angle of incidence to sine of the angle of refraction is a constant. This can be written as sine I by sine R is constant and is known as Snell's law. The constant in this equation is called the refractive index of the second medium with respect to the first medium, and is denoted by N21. N21 is a characteristic of the pair of media for a given wavelength of light and is equal to the ratio of the speed of light in medium 1, V1, to the speed of light in medium 2, V2. Let this be equation 2. By using equation 1, we can write N1 is equal to C by V1 and N2 is equal to C by V2. Therefore, V1 by V2 is equal to N2 by N1. Using equation 2, N21 is equal to V1 by V2, which is equal to N2 by N1. If N12 is the refractive index of the medium 1 with respect to medium 2, we can write that N12 is equal to V2 by V1. From these two equations, we can conclude that N21 is equal to 1 by N12. Now, consider a case where a ray of light first travels from medium 1 to medium 2, and then from medium 2 to medium 3. Let N21 be the refractive index of medium 2 with respect to medium 1. N32 be the refractive index of medium 3 with respect to medium 2, and N31 be the refractive index of medium 3 with respect to medium 1. If V1, V2 and V3 are the speeds of light in the three media respectively, then we have N21 is equal to V1 by V2, N32 is equal to V2 by V3, and N31 is equal to V1 by V3. V1 by V3 can also be written as V2 by V3 into V1 by V2. Therefore, N3, 1 is equal to N3, 2 into N2, 1